Okay, so we're going to talk about sequences. So there are two types of sequences. First one is going to be called arithmetic. So this is a sequence with an addition or subtraction sequence generator. So that word means this is what I do to each term to get the next term. So no matter what the sequence is, the generator is what I'm doing to go from one term to the next. Now, in these sequences, the number added to each term to get the next is called the common difference. So this is the general equation we use. M is the common difference. And B, it's important, B is we call it the zeroth term. So it's the term that comes before the first term. So let's just make sure. We'll talk about that in a second. Now we use this notation. So f of x is for functions, so t of n is for sequences. And notice how an arithmetic sequence looks like a line. Well, that should make sense because in a line, I'm adding one y values. To get from one y value to the next, I'm adding the same or subtracting the same. So that's what a arithmetic sequence is, essentially the outputs of a linear function. Geometric sequences are sequences with a multiplication or division generator. So these are ones where I multiply or divide to get from one term to the next. The number applied by each term to get the next term is called the common ratio or multiplier. So I will be using this. And notice how multiplication, well, this looks like a exponential function. So B is the multiplier. So please notice the difference in what B represents from geometric to arithmetic. And then A is the zeroth term. Okay? So we're going to look at a problem to kind of get an idea about these sequences. Okay. Problem 1. Here's the problem. Consider this sequence that begins 300, 180, 108, 64.8, ... That means the sequence goes on forever. So let's just make certain we're aware of one thing. Remember how we use t of n? Well, this would be the first term. So this is t of 1. This is second term. This would be t of 2. This would be t of 3. And this would be t of 4. So we always name the first number in a sequence is the first term. Okay. Now, based on this information, can this sequence be arithmetic? So let's answer that question. So to be arithmetic, right, I have to have a common difference. So that means I have to be adding or subtracting the same amount from one term to the next. So in this sequence, if it was arithmetic, I'd have to be subtracting because I'm going down. So to get from 300 to 180, let me do that. So what's 300 minus 180? Well, that's 120. So I'd be subtracting 120. So to be arithmetic, I'd also have to subtract 120 from 180 to get the next term. So if I take 180, subtract from it 120, I get 60. Well, the third term is 108, so this can't be arithmetic. Now, geometric, it's kind of this. So geometric, I have a multiplier. So I have to be multiplying or dividing to get from one term to the next. So because I'm going down, that's division. So what do I divide 300 by to get 180? Well, that's easy. I'm going to find out what 180 over 300 is. So my calculator, I get 0.6. So that would be the multiplier. So we're going to see if that's the case. So in order to get from 180 to 108, I have to be able to multiply 180 by this number to get 108. So 180 times 0.6, I get 108. So that looks pretty good. So now to get from 108 to 64.8, I got to multiply by 106. And so I multiply that by 0.6. And I get 64.8. So it looks like this is geometric. And the reason? Well, it's geometric since it has a multiplier of 0.6. That's why. Okay, now the same sequence. Now we want to assume it's geometric, so let's plot the sequence on the graph. So here are the first 4 terms. So you can see term 1 is 300, term 2 is about 180, term 3 is about 108, term 4 is about 164.8. So we got to find 5 and 6. So T of 5 is going to be 64.8 times 0.6. So get my calculator. And that is 38.88. So I'm going to find that. So this is 25, 50, so 38 is going to be a little about, it's going to be about halfway, right? So the halfway point between 25 and 50 is 37. So it's going to be a little bit above half. So it's going to be about right here. Okay. Then to get the 6th term, I hate when that happens on these. To get the 6th term, I'm going to multiply 38.88 times 0.6. So 38.88 times 0.6 is 23.328. So it's going to be right below 25. And so there is those terms plotted. Notice how, if I were to connect the dots, it forms an exponential function. So geometric sequences when graphs should look like exponential functions. So then this is the term number, and this is the value of the term. Okay, last problem. Will the values of the sequence ever become 0 or negative? Well, this is what we know. So let's look at our knowledge of exponential functions. So, because geometric sequences look exponential, so it's 300. And so this graph, as you saw, it starts here. And it's going to be coming down, 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 right? So from our knowledge of exponential functions, we know that this will approach the x-axis but never touch. And why? Well, as I keep taking 60%, so 0.6 is the same thing as 60%. As I keep taking 60% of a number, I will always get a number back. And because these numbers are always positive, no matter how small I get, so for example, if I took 0.004563, that's a really small number. Right? That's almost 0. But if I multiply that by 0.6 or determine what 60% of it is, I still get a number. I get 0.002778. I get a smaller number, but it's still technically not 0. And so these numbers will never ever become 0. And they'll never become negative because 60% of a positive number is going to be positive, no matter how small it is. So there's a little review or introduction to sequences.